In this video, I'm going to show you how to use exponential functions to model situations. Now, the formula that I'm going to use looks something like this. So I've altered the original a little bit. So we have a times a naught times b to the power of t over t. So originally we had y equals c to the power of x. What I've added here is a is our final amount. A naught is our initial amount. In other words, it's kind of like our stretch. I've changed the c to a b, and I've called that our growth or decay factor. Now, the growth or decay factor has to be a fraction or a percentage. Remember that it shows you how much remains or how much it's growing by compared to the previous time. The t on the top is our time, so that's a little t, and the capital T on the bottom is the time to grow or decay by that factor of b. So, for example, if it takes 10 years to grow, then our denominator in that exponent would be 10. So let's say we have 30 years, then 30 divided by 10 would be 3. So that means that we're growing 3 times. So that's why our exponent would be 3. So remember that the bottom t is the time to grow or decay, and the t on the top would be our total time. You have to make sure that these t's actually have the same units, whether they're seconds or minutes or days or years or whatever. So let's take a look at an example. The real estate board in a city announces that the current average price of a house in the city is $400,000. It predicts that average prices will double every 15 years. All right, so I'm going to circle the numbers that are important. So the numbers that are obvious are 400,000 and 15, but we also have the word double here, which also gives us the number 2. So let's label these numbers according to our equation. So the $400,000, that stands for our initial amount because it says the current average price. So this is our A naught. Double means that that's our growth and decay factor. So that's going to be our B. And because it doubles every 15 years, these two are related. So it takes 15 years for the price to double. So this is my capital T. All right, so writing the formula, we get A equals $400,000 times 2 to the power of little t, which we don't know that time, divided by t, which is going to be 15. And it takes 15 years again for it to double. So that's why the 15 is on the bottom. So the second question, it says predict the value of the house after 10 years. So after 10 years, it hasn't doubled yet. So when we calculate this price after 10 years, it shouldn't be $800,000 yet because it hasn't reached 15 years. So let's see what that value is. So it's going to be 10 to the over 15 as our exponent. And when we type this into our calculator, we're going to get $634,960.42. So you can see that in 10 years, it's estimated, I guess, about 2/3 of our time. It should be a little bit more than 2/3 more of 400. So that would be another, I guess, 230-ish thousand. All right, let me show you another type of question. And this is the one with temperature. So these ones actually are a little bit special. So let me read the problem to you here. A bottle of soda pop at room temperature is 22 degrees Celsius and is placed in a refrigerator where the temperature is 5 degrees. Okay, so the pop is 22 degrees and the fridge, the surrounding temperature, is 5 degrees. It is found that the temperature of the soda pop decreases exponentially at a rate of 9.5% every 6 minutes. Okay, so we want to use the same modeling equation. So A equals A naught times our base to the power of t over t. Now, what we need to do is we need to figure out what our base is. So we know that the temperature, it decreases by 9.5%. So after 6 minutes, it's going to be 100 minus 9.5%, meaning that it will be 90.5% of the previous temperature. So for example, if the initial temperature was 22 degrees, then after 6 minutes, we times that by 0.905, we will have that the temperature is now 19.91 degrees Celsius. Okay. So let's fill in kind of what we know. So we have A equals A naught times 0.905 to the power of T over 6. So the reason it's 6 is, remember, here's the every 6 minutes. 6 minutes related to my decrease. Now my A naught I kind of left out on purpose right now. So I want to show you something with the initial temperature. So the initial temperature states that when time is 0, my temperature is 22 degrees. So if I take a look at what the graph would look like, it's 22 degrees here, and it decreases exponentially. Now, the thing that we have to note is that it is placed in a refrigerator where the temperature is 5 degrees Celsius. Now, because the refrigerator is 5 degrees, it actually can't go below 5 degrees because that's the lowest the temperature is already. So we can say that there is an asymptote here at 5 degrees Celsius. Okay, so let me write that down. So asymptote at 5 degrees Celsius. So that means that the vertical displacement means that K is equal to 5. Now, this only applies to temperature questions because there is an outside variable that is influencing the temperature of that object. So what we're going to do is I'm going to rewrite my equation here, and we're going to figure out what that initial temperature is, kind of. We know that the initial temperature is 22, but because of the surrounding temperature, it changes it a bit. So we're going to say that at 22 degrees Celsius, we have A naught times 0.905 with an initial time of 0 over 6, and then plus 5. So when I calculate this, I actually get 17 equals A naught, and then 0.905 to the power of 0 is always going to be 1. So that means that my initial temperature is actually going to be 17 degrees. So when I write the exponential function to model this, it's going to be 17 times 0.905 to the power of T over 6, and then plus 5. So what you have to remember that whenever we're dealing with temperature questions is that this initial temperature, this A naught, is equal to 22 minus 5, or you have to think of it as the temperature of the object minus the surrounding temperature. So sometimes people call this as the temperature minus the temperature surrounding. All right, so now that we have this formula, this function, let's see if we can figure out the next and answer the next question. So what is the temperature of the soda pop after 3 minutes? So after 3 minutes, because the 6's are also already in minutes, we can go 17 times 0.905 to the power of 3 over 6, and then plus 5. So plugging this into my calculator, I get 21.17 degrees Celsius. So this should make sense because it drops by 9.5%, and 9.5% of 22, let's just put this up here, is 2.09 degrees. So it should drop, half of that should drop about 1 degree. Now remember, it's not linear, so therefore when it drops, it's up, I'm just saying approximately 1 degree. So it's 22 degrees, it drops approximately by 1 degree because it's 3 minutes instead of 6 minutes. So therefore it's about 21 degrees, which is now 21.17 degrees Celsius if we follow an exponential curve.